Tuesday is sequence now.
We already introduced continuity through that handout. You kind of know what continuity is. In calculus, you must always give this definition of continuity. And the order you prove them is important because if this doesn't happen, we don't care about these. Like each one builds upon the other. So a function is continuous at a number a if, by definition, the limit as x approaches a of f of x equals f of a. That has to be true. In order for that to be true, we kind of need to know if 1 and 2 are true. And 1 and 2 says it has to be in the domain. And 2 says the left-hand limit has to equal the right-hand limit. So the limit has to exist. It has to be in the domain. Therefore, the limit has to equal the domain value. It seems so easy. For whatever reason, it becomes difficult. To spit this definition back out at me is a struggle I witness every year. So again, highlight this, make it something that you know, circle it, because you have to regurgitate this definition from now to that AP test in May. All right, so if a function is not continuous from both sides, it can be what we call continuous from the left or continuous from the right. So we also have what we call right and left continuity. So you have left-hand continuous and right-hand continuous. It should make sense then that this occurs when the left-hand limit equals the function value, but the right-hand limit does not. So for example, that could be something like a piecewise where it's closed here and open there. This one would be an example of left-hand continuous because it's continuous from the left. The limit from the left equals the function value, whereas the limit from the right does not equal the function value or the left-hand limit. So this would be left-hand continuous.
But it's not continuous as a whole.
Correct. It's only left.
One side of the zero, or I'm sorry, the y-axis.
Not the y-axis.
The x-axis, the left side. So like left, right. The left side coming towards this point is continuous.
I think
coming from the left, you're continuous.
I think he understood it as from the left of the graph, like he's dividing it at the y-axis. You're dividing it.
You're dividing at the point of discontinuity. The jump. Yeah, not the y-axis. The jump of the graph. Sorry, thank you. I like how you know how Michael thinks. So you have to help me think with him. All right, a function is continuous on an interval if it is continuous at every point on that interval. At the endpoints of the interval, the function must be continuous from the right and continuous from the left. A continuous function does not need to be continuous on every interval of the function. So again, we're starting with a lot of definitions. We're going to look at pictures, and then we're going to do all the examples. If a function f is not continuous at a point C, then we say that f is discontinuous at C, and C is considered a point of discontinuity. We have several names for our discontinuity. So, infinite discontinuity is vertical asymptotes. So vertical asymptotes will be infinitely discontinuous because their graph is going to an infinity at a point of discontinuity. So that's kind of what you're witnessing here. Jump discontinuity is there are two varying definitions. One is here, and two is with a step function. So you can have jump discontinuity if you have a hole, but that hole gets filled in somewhere else along the graph. So we don't call this removable because it has a point that exists. It is only a removable discontinuity if that hole does not get filled in. So removable is when you have a hole. We get removable a lot when we factor, and we can cancel the factors. those create removable discontinuities. So like if you look right here, this x squared minus x minus 2, that's factorable. You can cancel the x minus 2, hence the vertical asymptote does not exist, it becomes a whole. And that's kind of where we were making that one mistake on our limit test the other day, is we saw this, said, oh, it's going to have infinite, but it doesn't because it cancels and becomes removable. Jump could be removable, so same function here, but now we created a piecewise to fill it in. Or the step function is also jumps, because you go fill it in, open, jump, fill it in, open, jump, fill it in, open, jump. Good? So given the following graph, at which values is it discontinuous, and what type of discontinuity are we witnessing? So going from left to right is the easiest way, and you just kind of follow the graph, right? So you go boom, 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 boom. Oh, I got a hole. So the hole occurs at x equals 1. I search up and down. The hole's not filled in. So x equals 1 is removable. Let's keep tracing. I get to a closed-in circle. In order to get to the next point, I got to jump on my paper from the bottom to the top. So that point occurs at 3. And that's jump. Open circle up top. Continues down. Oh, I get another open circle at 5. However, if I search up and down at 5, there's a point filled in. So x equals 5 is also jump. Now if we talk about continuity, at 1, its left and right hand are the same, but it's not in the domain. So no continuity at all. On number 3, however, we have left hand continuous because it's filled in from the left. The domain is the same as the limit on the left. So we could say x equals 3 is that left hand continuous. Just trying to show you examples of it. Yes?
So it's still left hand continuous even though there's a hole from the left?
The hole from the left is at 1. So you look at like small segments. So like in the left hand continuous, what needs to happen in order for this to occur is the limit as x approaches 3 from the left. So the limit as x approaches 3 from the left is whatever we'll call this value b.
It has to equal that.
It has to equal exactly of b. F3, sorry. Like the limit from the left has to equal the function value at 3, and they have to both equal b, whatever b is. So finding the points of discontinuity for the greatest integer function, you don't have to resketch it. It's on the front side, but if you want to see it sketched again, remember it goes from closed to open, closed to open. So you'd have closed here, all the way to open there. This is an example of jump discontinuity because the greatest integer function has jump discontinuity at all integer values. So remember, we use k to represent an integer. So there would be jump discontinuity at all x equals k. Because you're going to have a jump discontinuity at 1. You're going to have one at 2. You're going to have one at 3. You're going to have one at 4. 100. 1,000,000. Like, all of them are going to have jump discontinuity. So what you have to do is have to talk about this in terms of a k, where k represents that integer. So we'd say the greatest integer function has jump discontinuity at x equals k, where k is an integer in our domain. If you want to talk about right and left hand, this function is right hand continuous because the limit from the right will equal the integer as well as the value. So again, the limit from the left would equal k minus 1. The limit from the right would be y equals k. Y of k will equal k. Therefore, it's right-hand continuous. So again, I said, this stuff seems so, like, it seems like it should be so, like, basic, right? Like, it's just like, yeah, like, that makes sense. It's super logical once you can start to visualize the graphs. So the logic is there. It's just putting the logic to the graphs. And we'll walk through it together. Show that the function f of x equals 1 minus the square root of 1 minus x squared is continuous on the interval from -1 to 1. So again, this is a semicircle because it's only the negative side. So again, this is f of x equals 1 minus the square root of 1 minus x squared. So the negative implies it's the bottom of a circle. This is like our r, so it's a radius of 1. So it's a circle with a radius of 1, and then the 1 here, if you move it to the end, it would be a positive, so it's shifted up 1. So it's the bottom of a circle with a radius of 1, shifted up 1. What would the domain be then? So we know that anything under a square root cannot be beyond positive or negative, depending on the quadratic. So it's 1 minus x squared has to be greater than or equal to 0. Because we know a square root cannot be negative. So in order to find the given domain, you have to solve for 1 minus x squared greater than or equal to 0. That gives 1 has to be greater than or equal to x squared. So if you solve it out, you get that x has to live between 1 and -1. Think about it. If you plug in 2, is 2 squared smaller than 1? Like, so even if you square rooted both sides, you get that positive and -1, and then you just had to figure out if it lived in or out, but we could know, kind of based off this, it has to live in. Are we okay so far with domain? So this is like a continuity on an interval. Because it can't live beyond that interval. So we talked about what it looks like. We know it's a radius of 1. So a radius of 1 usually goes from here to here and down 1. But now the graph is shifted up 1. So instead of being here at 0, we'll be in the center at 0, 0. Plug in 0. 1 minus 0 squared is 0. Square root of 1 is 1. 1 minus 1, 0. Plug in your endpoints. 1 squared. So you have 1 minus 1 squared. So you get 1 minus 1, 0. 1 minus 0, 1. So the endpoints will be at 1. So we can see that circle of radius 1. And it's only the bottom because it's only the minus. Is it continuous on the interval? Are there any points where it's not going to exist? So how do I show that? Well, the only way to be continuous on an interval is for the left hand and the right hand endpoints to be the same. So you have to show that the limit as x approaches -1, so you're going to come from the right, equals f of -1. So does the limit from the right equal the value on the right? And what do they equal? Yep. Now y'all look at left-hand continuity. And again, as you come from the left, does it equal the value at that point? Yes. So in order to be continuous on an interval, you have to have left and right-hand continuity coming towards the endpoints. That's what the definition of continuity on an interval says. Good? Okay, I know how much we love piecewise. Take a minute and graph yourself out these three functions. So piecewise functions are like the ones that matter for continuity the most because typically they're the ones where we have our issues. So we'll graph the first part. We're graphing x plus 1 for all x values less than or equal to 1. So I need to know where does it start at 1. So plug in 1. 1 plus 1 is 2. So at x equals 1, the y value is 2. It is a closed circle because we are equal to. The slope of the line is positive. The y-intercept is 1. So it's kind of going down, it looks like, and forever. The middle is 1 over x. Now, looking at 1 over x, I'm like, oh, there's a vertical asymptote at 0. However, is that interval included here? No. So don't got to worry about the continuity of that. But I do need to find the beginning and the end. So plug in 1. 1 over 1 is 1. So at 1, we're at 1, and it is an open circle. At 3, you're at 1/3, and at the middle of 2, you're at a half. So 2 is a half, 3 is a third. So I have a slight little curve. Both are open circles at beginning and the end. Picking up at 3, 3 minus 3 is 0. Square root of 0 is 0. So I have a closed circle here. 4 minus 1 is 1, so it goes here. The next nice point to plug in would be 7. 7 minus 3 is 4, and you get 2. So is this graph continuous on its domain? No. How many points of discontinuity do I have?
2.
They usually occur at the endpoints of a piecewise. So at x equals 1 and x equals 3, I have points of discontinuity. What type of discontinuity are they? Yep. And then the question is, okay, are they continuous from the right, left, or neither?
The first one's left, the second one's right.
Perfect. So this will be from the left, because the left-hand limit will equal the function value. And the second one will be from the right. Okay, does the following function have removable discontinuity at x equals, I think it should say -2. If the discontinuity is removable, Find a function g that agrees with f of x or x equals -2 and is continuous on the real numbers. So again, sorry, missed my negative sign. Does yours have it? No. It should definitely be -2. It wouldn't make sense to be positive. So what do we want to do? First, you want to factor the numerator. So what do you get? Perfect. X minus 4, x plus 2. So what happens? They cancel. So then the question is, does it have removable discontinuity? Yes. So at x equals -2, we have removable discontinuity. That means this function here really behaves like this. So it says find a function g that agrees with f. So what we're doing is we're going to create a piecewise function. We're going to call it g that's going to fill in that hole.
Yes, you write the f of x one.
So exactly, we have f of x, and we can write it either as the original or as the simplified. And then we're going to do is say that x does not equal -2.
And then
We need to figure out what can I fill in so that this is continuous. Well, what do you know about the definition of continuity?
it's
That the limit has to equal the value. So how can I find this value?
just on the limit.
I find the limit as x approaches -2 of f of x, which in this case is like finding the limit as x approaches -2 of x minus 4. So I get -2 minus 4 or -6. So the limit is -6. Therefore, to fill it in and make it continuous, the function needs to be -6. So again, that you could write the x minus 4. You want to be super lazy. You could also just write f of x and then put the -6. It's not wrong. Everything is about efficiency. What makes you the most efficient? So if writing f of x makes you more efficient or less likely to make a mistake,
Would that mean if you do put f of x, you have to put x is non-equal to -2?
Yes.
Okay.
Good question.
yes.
So when you're finding the removable discontinuity, it is that x is equal to -2. So how is the -6 involved in?
'Cause
So on a graph, I'll go over here.
Doing the math makes
If you were
sense.
going, yeah, if you were doing this as a graph, f of x would look like this. It would go, have a y-intercept at -4. It would go up one, right one, up one, right one, up one, right one. And then at -2, that graph would have a hole. This is f of x. If f of x were graphed, this is f of x. Okay? So right here, at x equals -2, there is a big, fat hole. And that hole, oops, I need another line, has at -6 on y. So what we did is say, okay, here's a piecewise function. It's still f of x. But what I'm going to do is I'm going to create this new part of it and say that at x equals -2, it's -6.
The y values.
Yep. So I fill in the hole. That's what we've done with this piecewise. We've filled in the hole. The hole gets filled in with the limit. The limit fills the hole. So if F and G are continuous at A and C, you don't have this. It's just me summarizing for you because, again, continuity is so easy, but yet we, you know. So if F and G are continuous at A and C is a constant, then the following are also continuous at A. Any polynomial is continuous everywhere. Any polynomial is continuous everywhere that it is continuous on all reals or negative infinity to infinity. Polynomials are continuous. What are polynomials? Any function, be cubic, quadratic, quartic, quintic, as long as there's no division and no multiplication of multiple variables. Or anything to a power that is not a whole number. So that's the definition of a polynomial. No division, and no fractional exponents, and no multiplication of two variables. A rational function is continuous wherever it is defined, i.e. on its domain. So a rational is not continuous at 0 because it's not included on its domain. The following are always continuous on their domain. So what I want you to do for tonight is page 84 and 85. We're doing 1 to 5 odd, 11 to 18 all, and then 21 to 29 odd. The 11 to 18, I think, again, you're matching up some stuff. I usually do the alls when you have to do the alls.